Hello everyone and welcome to chapter 4, which talks about integration. Suppose we have this function here and we were asked to find the area under this curve here. Usually we can't do that using the mathematical formulas that we already know. This is where integration comes in handy, because integration gives us a set of tools that we can use in order to find that surface area. So before we dive into how to find that surface area, we need first to know what integration really is. So we start with 4.1 and we talk about antiderivatives. So what are antiderivatives? The word derivatives is something that we already saw back in when we talked about differentiation. So when we add the prefix anti to the word derivatives, we are just trying to do an operation that is opposite to differentiation. What I mean by that is that if we had a function, let's say x squared, usually when we differentiate the function x squared, we will end up with 2x. So if we have the function x squared and we want to apply antiderivative to that function x squared, we are trying to do something that is opposite to differentiation. We are trying to maybe go back to a function that is, let's say, original, or that a function that was the source of x squared that we used to have before we had x squared. This is what we mean by antiderivatives. So we had an original function, we differentiate that function, we have our current function, and then we can differentiate our current function further to have another function. So to illustrate that, let's say that we have the function f. Let's say that we have the function f of x equals to 3x squared. And we want to find what was the original function that we had before having 3x squared. That original function that we differentiated first before reaching 3x squared. Using our prior knowledge, we can see that 3x squared might have come from x cubed. If we were to differentiate x cubed, we'll end up with just 3x squared. And that's really what we have here. So x cubed is we can say that x cubed is one of the antiderivatives of 3x squared. And we call this function 3x squared, we may call it a big f of x, which is x cubed. This is the antiderivative of 3x squared. Because as I said again, if we were to differentiate this function here, we just end up with 3x squared, which is the same as this. And this is what the definition of antiderivative says. It says that a function f is an antiderivative of small f on an interval I when f prime of x is equal to f of x for all x in I. This means that, again, the function f that we had is x cubed. The function small f that we had is 3x squared. So to go from here to here, if we were to differentiate f of x prime, this will give us 3x squared. If the result that we found here is the same as the result that we have already in f of x, then we can come and say that big F of x is an antiderivative of small f on all values x that are in I. So far we saw that big F of x equal to x cubed is one of the many functions or many antiderivatives of 3x squared. This also means that there might be other functions other than x cubed which are also antiderivatives of 3x squared. So let's say, for example, the function x cubed plus 6. This also, if this were to be differentiated, will also end up with 3x squared. Another function again, x cubed plus 1 will also give us 3x squared. So if we take x cubed plus any constant, whatever the constant is, we'll always end up with 3x squared because the derivative of the constant is just 0. This is why we can write the antiderivative in a much more general form than just writing x cubed. We can say that the general formula of the antiderivative can just be, let's say, f of x plus a general constant, and we can call this constant c. So the general form for the antiderivative of, let's say, for f of x equals to 3x squared is x cubed plus c, which is a constant. We can say that c is in R. This is what the theorem here says. It says that if a function f is an antiderivative of small f on an interval I, then g, which is another function, is also an antiderivative of f on the same interval I if and only if g is in the form f of x plus c for all x in I. What I mean by that is that if we had f of x, as I said, which is equal to x cubed, and then g of x, which is equal to x cubed plus 1, then we can write g of x as just f of x plus 1, and then this one here is just this constant here. So I can write the general formula for antiderivatives as just g of x equal to f of x plus a constant, where f of x is just the most obvious solution for the antiderivative that we usually find. But f of x can be any solution. Let's say if we had f of x minus 1 here, then we can go from f of x to g of x just by adding 2 here instead of 0 or 1. It depends on the values that are different, the constants between f of x and g of x. How is this illustrated in graphically speaking? So if we had a function y equal to 2x plus c, so if c is equal to 0, we'll just end up with this line here. If c is equal to 1, we'll end up with another let's say another function that shall go from here, or maybe in this case it's c equals to minus 1. Yeah, if c is equal to minus 1, we'll end up with this function here. If c is equal to 2, we'll end up with a function with this function here. So we'll end up with just parallel lines that will have the same slope, because if we differentiate this y equal to 2x, we'll end up with just y prime is equal to 2, which is the slope of all these functions. So antiderivatives in general are just functions that are more or less parallel, if we can say that. If they are lines, they'll be parallel. If they are, let's say, curves, they will be, let's say, displaced. One is, let's say, higher or lower, or something like that.